telescope or sometime observing remotely, and also coming at least once per year with my student. Students at UC Santa Cruz are very lucky because they can have access to 1 meter or even the 3-meter telescope. So, but I never been here for lectures, so I'm very happy to discuss about the extreme universe today. So before going to the extreme part, I want to start with some astro news. If you are interested in astronomy, you might have seen some of this recent news, really a milestone in astronomy. So the Rubin Observatory started to get operational just a few weeks ago. Actually, I think it was about 10 days ago. And they have the largest camera in the world. So this is a 3 metric ton camera with about 3.2 billion pixels. And here, actually, this camera was designed and assembled pretty close to here. This picture is taken in the SLAC, the Stanford Linear Accelerator Laboratory. So it's kind of a local-ish project. Of course, this project like this, there's multiple countries involved, but that's really, really interesting. Here, they released 2 images, actually, over the last weeks. Of course, I didn't take the full resolution. It's very heavy. But this image is the highest resolution single picture ever taken. So you can really zoom in. You can see multiple things. So what's the purpose of this telescope? So it has a very large field, as you can see. And it can really, if you take 2 pictures at different days, you can see that some points are going to move from one picture to another. So this is a very good tool to detect a lot of asteroids, a lot of transient. Also, if there's supernovae flare, again, they compare 2 pictures, and they will see what's happening in the sky. So it's a good telescope to trigger multiple other telescopes to follow up for any interesting event. So that's a good opportunity to start with this telescope to introduce about light, because we're going to speak about high energy, gamma ray, but before we need to go through the electromagnetic spectrum. So here are the color that you can see with your eyes. That's the color of the rainbow that go from the purple up to the red. I think this working here. And what you have to know is all of these colors correspond to different wavelengths, different frequency of the photons, of the particle of light. If you go to the red parts, it's longer wavelengths, lower frequency, and also lower energy per photons. The more you get into the blue side, the higher energy, the higher frequency, and the shorter wavelengths for the photons. So what's interesting also about the spectrum is correspond to the maximum of the sun emission. In this plot, you see the amount of light radiated by the sun at different wavelengths. And it's not really a coincidence that the visible spectrum we observe is actually at the maximum of the emission of the sun. What is interesting is our eyes. The sensitivity of our eye evolved over a million of years, and this is the curve of sensitivity of our eye really aligned with the emission spectrum of the sun. That means if we were humanity in a different planet with a different star, we probably will see the color totally in a different way. Anyway, so if we're moving from the Rubin, you can also build color image with this telescope like the one I showed before, but it's not like the eye. We don't process everything at the same time. You have to use different filters that are going to let pass different wavelengths. This is actually it's a gigantic filter for this huge camera. Most of the filters are just a few inches wide, like this, because you just need to put on top of the detector, but the detector is so large. So you have the different passband here that will tell you that the filter allows only the green light to pass through, only the blue light, or only the red light. And if you combine image, you can have this beautiful color image. So that's it about the introduction about visible light. So now I want to extend a bit through the full electromagnetic spectrum. So what we see with our eye is a tiny, tiny fraction of the full spectrum of the photons. There is so many more energy wavelengths that we will never be able to see with our eye. We can start from radio wave up to microwave and infrared. So radio wave are the one with the largest wavelength, the lowest energy. And if you go up to higher energy, you go to ultraviolet, X-ray, and gamma rays. And with telescope, at least we tool, we can observe the sky in all these different wavelengths. So starting with a radio wave, for this energy range, the photons behave as wave. You need to have a wave detector. So what is a photon? It's a vibration of the electromagnetic field. So that means that the charge, the electricity is going to vibrate. If you have rods like this with free electrons in this, so just a small current in this, the electrons in this rod are going to vibrate at the same frequency as a radio wave. And if you amplify the current, then you can get a signal, electric signal. So this is a perfectly legit telescope, and you can really observe the sky with this, even if it doesn't look like a real telescope. Then if you move to the optical part, here you can take both the fact that photons are particles and waves. They are waves, so you can have mirror and you can reflect the wave, but the CCD, like the same CCD camera that you have in your phone, it's a particle detector. That means the energy of the photon is going to be released, to be transformed in an electron, in a charge, that then can be read by a detector. And if you go further in higher energy, here, the photon doesn't behave at wave at all. Actually, the wavelength of this particle is smaller than the size of an atom. So it's impossible to reflect that. Actually, if you build mirror, the gamma rays are just going to pass through your mirror, are going to pass through your detector. So you need to find a way to catch this particle. And an example here of the Fermi Space Telescope is basically just a cube, 1 meter cube in space. And the particles are going to arrive here and be destroyed. They're going to interact with a high density material inside and release their energy in secondary particles that are going to be detected. So that's a way where to detect this particle, you need them to be totally destroyed in your detector and quantify the energy remaining. So that's the part we're going to discuss about today. So now is this a different view of the universe? Actually, the Earth is constantly bombed by all these very high energy particles that are invisible to us, but also that is very nice that we cannot access to them because these are a lot of energy, a lot of radiation, and if we were exposed to this particle, that could be very harmful for us. You can consider like the universe as an extremely radioactive environment. So we are fortunate that the Earth protects us in two ways. There is first way, there is a magnetic field of the Earth that's going to deflect this particle. Most of these particles are charged, and that means if you have charged particles, they move, they are deflected by magnetic field. So they will be deflected in both directions, and some of them will be trapped here in what we call the Van Allen belts. So these are very high radiation zone around the Earth here, like lobes. And when people send rockets, usually they avoid to go through it. It could really damage the electronics of telescopes, space telescope or satellites. And especially if you send human, like if you look at all the humans were sent to the moon, they were avoiding to get this zone and also avoiding time where the sun was at high activity. So the second barrier here is our atmosphere. Now, our atmosphere is actually much more efficient than that. That means the particles are going to disintegrate within the atmosphere, and only a very small fraction of them will reach the ground. So, for example, there is discussion about going to Mars and a colony there. Well, in Mars you have two issues. You don't have this, and you don't have that. So, again, that's very challenging. Or in the moon, it's even worse. Anyway, there is a few particles that still reach the ground, and we can measure that. So the very first experiment that detected we have some particle in the air was made by this guy, a French guy, it's Coulomb, it's, more than 200 years ago, Charles de Coulomb, that has this device called an electroscope. So how does this work? Here you have a rod that is charged positively. Let's say if you rub against leather, for example, it's going to remove some electrons and they're going to charge positively the rod. And here you have a conductive metal here, and that's split into gold leaves. So two gold leaves at the end. So they're very sensitive, and you have a vacuum here. So it's really isolated from the outside. If you put a charge here, then this is going to be negative because this part is positive, and the end here will be positive. So the two gold leaves are positive, they're going to move away from each other. It's like you have two magnets, plus and plus, and you see they repel each other. So if you do this experiment, you will expect that this is very steady. I mean, there should not be much discharge, especially this is in a vacuum. The thing that Charles de Coulomb observed that the two gold leaves were slowly going back together. And there's not many ways of explaining that besides that there must have been some charged particle just crossing here, crossing the vacuum or the barrier here and interacting with the setup. So he had some intuition that there have been some charged particle in the atmosphere, but had no idea where this particle come from. The big discovery about the origin of this particle is usually attributed to Victor Hess in 1912. The idea is there have been a big debate. They were thinking that this comes from the ground, and they were right that most of the radiation we have today, if we're here, come from the rocks behind us. But he was expecting that going up and up in the atmosphere, he would see less and less particles, and he would really quantify that, yes, they all come from the ground. But what they observe is if you move about 1 kilometer, altitude is just slightly decreased, and if you move up and up, then all the particle rate increase faster and faster, which means with an electroscope, you will see the discharge time getting faster. And with this experiment that showed that, yes, there is some radiation from the ground, but there is also a huge amount of radiation coming from the space. So that is what we call later cosmic rays. So cosmic rays was a term invented by Robert Millikan. Actually, he got a Nobel Prize about electricity and charged particles. And here is kind of the mix of what is falling on Earth. So the first thing is cosmic rays. It's a very misleading term. These are not rays. When you say rays, like light rays going straight, these are charged particles, and these charged particles are deviated by magnetic field. So this doesn't go straight. So it's more particles than rays, but the name is here and we cannot do anything about that. So the abundance of it, the very large party are single protons or hydrogen nuclei. You also have some higher nuclei here, helium nuclei, so it's 2 protons, 2 neutrons, a bit of electron, and then there's hundreds of different heavier nuclei. It's a really big scientific topic of doing the chemistry of cosmic ray. You can learn a lot about the universe by looking at the different fraction of elements here. Okay, so now we see a bit what are cosmic rays, and I'm going to see if you're following and ask you a question here. What is this image? It's very hard because even my colleague, I asked a bit a few days ago, they were very confused by that. So if you have some idea, raise a hand. I will help you a bit. So if you're an astronomer, you will see that this unit, alpha and delta here, are actually coordinate units in the sky. So this is a sky map. Actually, I can give you that here the units are in degrees, so it's a sky in degree. So that's a sky map where you see something, and you see something relatively unusual, because then you look at the scale here, that's the intensity, so you have a hole in the sky. You have like a very low intensity region surrounded by a very high intensity region. So there is something here that is not usual. So I can help you more. This is a cosmic ray map of the sky. Yes? Is it the sun? No, it's not the sun. No, but you're pretty close. You're getting close. Yes? The moon. That's the moon, exactly. That's the moon. Congratulations. That's the moon, and this picture tells us multiple things. That tells us that first, the cosmic ray are just created in the high atmosphere. They are created in a space farther from the moon. So basically, it's a shadow of the moon in cosmic ray on Earth. Another very interesting thing is the exact position of the moon is here at 0, 0. But the shadow is here. And here, that's the same thing I just mentioned before. The cosmic rays are deviated by magnetic field. The Earth's magnetic field is actually bending the cosmic ray. And we see the shadow of the moon that is just not at the right place if it was light ray. So that actually, if you quantify this deviation, you can even quantify the magnetic field of the Earth. So that's pretty neat. So cosmic rays are great, but when you do astronomy like me, you like to observe objects, this is pretty bad because the magnetic field is just blending everything. So this is an example here. You have a source here in this side of the galaxy, and the cosmic rays are going to do all that and reach here. So you're going to see in this direction, even if the source is in that direction, or everything is mixed. And so this is a map of the sky of very high energy cosmic rays. Well, you see there is some excess here. We believe it's come from a cluster of galaxies, but you cannot really see anything. So this was taken from the southern hemisphere with the OJ telescope. And this comes from here. If you have a magnetic field, an electron or charged particle, it's just going to rotate around. So it's very nice to count particles, very bad to do astronomy. Yes? So these are particles, charged particles. Like an electron can be a cosmic ray as soon as it propagates at high energy in the universe. Yeah, I mean here that's mean that this one, the electrons get deviated by the magnetic field of the galaxy and it's just going to wander around. At some point it's going to reach the Earth, but all the information about the direction is lost. Okay, so now getting a bit closer to what we can do on Earth. So there is this air shower. I say that this cosmic ray, when they interact with the atmosphere, they're going to disintegrate. And this disintegration path can be complicated, especially if you have heavy nuclei, can disintegrate in many different particles with very short lifetime. So here you have pions, the neutron, electron, neutrino. I'm not going too much into the details about that. But this phenomenon of disintegration up to billions of particles in the atmosphere that were discovered by Pierre Auger. And if you were paying attention, the Pierre Auger collaboration. So they have a very nice telescope in South America. So that's what we call air shower, and there is only few particles that can really reach the ground. These are muons and neutrinos. There are a bit more physics here, so brace yourself a bit. So here, a bit more about what happened when you have disintegration. Let's say you have a gamma ray. The gamma ray is going from the universe, is going to interact with a particle of the atmosphere. It's going to interact with the nucleus, and this creates a split of two particles, electron, positron. Positron is the antimatter of electron. These two particles are still packing a lot of energy. And since they are charged, when they pass around another particle of the atmosphere close to the nucleus, they're going to be deviated strongly. We call that the branch-swallowing radiation. And so this emits another photons, and if this has enough energy, it will be another gamma ray. So you can see the process, the gamma ray split in electron, positron, they then emit a secondary gamma ray, split again, and at each step, you decrease in energy. So at the end, you exhaust all the energy, and fortunately for us, before it reaches the ground. If not, we will suffer the radiation from that. Saying this, if you're in high altitude in mountain, you still have this. Actually, pilots of jets or plane, they have a radiation dosimeter because they have radiation just being in the plane. You have more radiation due to this. And this is the one for nuclei, proton, and this one is more complicated. The only thing you have to see about the difference is the gamma ray is pretty narrow, and the proton ion is just very spread out. So you can still make some difference. What is interesting for us is the gamma ray, because the gamma ray goes straight. They're not bending because they have no charge. Okay, so how do we detect this? I just say that this doesn't reach the ground, but somewhat we're still building telescope in the ground to observe this. So there must be a trick here. So this is a Hess telescope. It's an array of 5 telescopes in Namibia. I've been lucky to work with them several years ago, and I spent 1 month in the Namibia desert to take data with this huge telescope. It was a very nice experience. This is the largest telescope with mirror in the world, operational. So, and that's an information that is not very known actually, because when you think about telescope, you think about the maybe the VLT or big optical telescope. Now, the largest in the world so far is still this one. Okay, so what is the trick to observe this from the ground? So we need to go toward a bit more physics about what happened to these high energy particles. So one thing we need to remember here is that the speed of the light is not the same if it's in the vacuum or in the atmosphere or in the water. If it's in the water, the light is moving slower. We call that the refraction index that also bends the light. If you see the water, you will see that the image is distorted. And this is linked to the fact also that the light is slowing down. So you cannot go faster than the speed of light in vacuum. This is clear. But you can go faster than the speed of light in a medium with a refraction index, which means in the atmosphere or in water or in glass, you can have high energy particles that go faster than the speed of light. And this triggered a very interesting effect that was discovered by a scientist called Cherenkov, and we call that the Cherenkov effect, which is basically like a sonic boom of the particles. Let's say if you have a plane going faster than the speed of sound, you're going to have all the sound waves that are going to be packed here in one big cone here, and when this cone passes through, you hear a big boom of the jet flying. Well, that is the same here. The particle is going down, and is packing light, a cone of light, and you have a bang of light that's going to propagate through the ground. So you can detect this light, this Cherenkov light, with telescope. So, of course, there was no Cherenkov telescope at this time, so it was discovered mostly from this nuclear radiation pool. That's probably the main place where you can see for real with your eyes Cherenkov light. So there was wondering, what is this blue light coming from this radioactive element? And that's how they understand this. By the way, if you happen to fall in the water, you should probably still safe. Water is a very efficient radiation shield, and I took this from XKCD, doing very nice drawing that they should all be safe as soon as they're not going too close here. The radiation decreases very fast. So if you're really touching the road, yeah, you're probably going to die. But as soon as there's no isotope floating in the water, you should be good. So that's it about Cherenkov light. So now let's speak a bit more about the instrument and the method to detect it. So we have these high energy particles interacting, creating multiple secondary particles. They move faster than the speed of light, and they create this bang of light. It's just a few nanosecond emission. So the challenge is, this is very faint and very fast. You need to have a camera that can catch a nanosecond emission. To give you an order of idea, a nanosecond is about the time the light goes from me to about a few meters away. So I'm like a nanosecond from you. So it's very specific technology, and you also need to have large telescope. Another thing is you want to have multiple telescopes to do kind of triangulation. We call that stereoscopy, where you have you see the shower at multiple angles, and then you can reconstruct the direction. So you can see the light here. You have a light pool on the ground here, just a flash, and you will see this in your camera. You can parameterize here. We call that HELAS parameters. I'm not going too much into the details. And from this, you can reconstruct all the direction and the energy of the primary particle there. So I work mostly, I work with HES before. Now the telescope and collaboration I work with is the Veritas. So Veritas is an array of 4 Cherenkov telescopes located in southern Arizona. So really south of Tucson, just it's about 10 miles, 15 miles above the border with Mexico. So very dry area, beautiful sky. If you travel around this part in Arizona, you will see in the top of each mountain you have telescopes. It's the best place in continental US to observe, to do astronomy. So this observatory has been operating since 2006. Actually, the very first Cherenkov telescope was developed here in Arizona in the same observatory. We call that the Whipple telescope. It doesn't exist anymore. And that's interesting because they had this idea, okay, theoretically, we can measure gamma ray. So it was built in the 60s, and the first detection was in 1989. So can you imagine you work more than 20 years in your instrument? Because it is so challenging. I told you, you need to have this nanosecond camera. It's, especially at this time, it was a big challenge. So how they dealt to have the technology? Well, they went to see particle physicists. And in particle physics, in your detector, you have what we call photomultiplier. These are detectors that can detect a single photon and send a pulse. So it's very interesting. So what they've done, they packed many photomultiplier and put that in a focal plane and create a camera. So it's a 499 photomultiplier, and we have a field of view about 3.5 degree. So with this is an example of one event, like one gamma ray of high energy going through the telescope. Each of the telescope will have this pixel that fire up. And if you prolong or fit with a line to the ellipses, you will see that this is the position on the ground where the gamma ray should have landed. So you can reconstruct it and you can pinpoint. If you reconstruct many, you can build sky map of the sky in very high energy. So what do we see? This is the full sky, and each point here is a very high energy gamma ray source. So far we have more than 301 detected. And there's many of them, and all of them are attesting something very violent. You need to accelerate this particle up to very high energy to radiate. So you need some very strong particle acceleration process here. In our galaxy, you see this is our galaxy, the line here. You see there's a lot of sources in our galaxy. So we have our center, the supermassive black hole in the center of our galaxy. It's pretty bright. Supernovae or remnant, pulsar with nebula, X-ray binary, microquasar. And all the points that you see outside the galactic plane are coming from distant other galaxies. And here is mostly star-forming galaxy, active galactic nuclei, and gamma ray burst. So here I put some images. We can discuss after if you have questions about this, but I will not have time to cover all of them. So I will cover the one that I'm really working on and I enjoy the most, which are this one, the active galactic nuclei. You might know them under the term quasars. Quasar is a much more popular name, even if quasar is not super accurate because it's only a subcategory. By the way, this is an artistic view, right? So I hope one day we could take a picture as beautiful as this one. But so far, we have to deal with this. Okay, so let's speak now a bit where does gamma ray come from and how you produce gamma rays. So this is the closest AGN from us. Centaurus A, if you look in optical light, it looks like relatively standard galaxy, actually not super beautiful compared to many others. So there's a lot of dust here, kind of warped disk, and you have a big bulge of old stars around. It becomes much more interesting if you start to look at it in X-ray and radio. So if you shift in X-ray and radio, this is what you see. And here there's a totally different story. You see these two gigantic jets of plasma shooting in two directions, even larger than the galaxy itself. And this one actually is impacting the outside medium it creates. We call that a bow shock, a shock where you have a lot of radiation particle acceleration. So about 10% of the galaxy are, we call that active. That means the nuclei is very bright compared to the galaxy itself. And about 10% of them show this jet. So about 1% of all galaxies in the sky are this type of active galactic nuclei. So what happened? Oh, you have this jet? Well, we know that we have a supermassive black hole in all galaxies, in the center of all galaxies. So some of them are active. What does that mean? A supermassive black hole active. That means there is a lot of matter falling in it, feeding the black hole, and this matter is rotating around. The closer it is, the hotter it is. So this is a general scheme. So at large radius, you have mostly dust, relatively cool, just a few tenths of degree. And closer, you go to 1,000, 10,000, up to 1,000,000 degrees, very close to the black hole. Everything is rotating, got very hot. And this really radiates a lot. And for some of them, you also have jets. So the jets is mostly some particle just before falling to the black hole can be accelerated through very strong electric currents. You have to consider that you have a plasma of charged particles rotating very close to the speed of light before falling the black hole, and this creates ginormous magnetic electric field, and so some are going to escape at very fast speed. So this is a real image of a supermassive, active supermassive black hole. Was done by the Event Horizon Telescope, so really one of the images of the century. Finally, we've been able to take a snapshot of it. The technology behind it is amazing. It's too bad I don't have time to discuss much more about that. But what you can see here is the scale of the thing. So these black holes are between million to billion times the mass of the sun. And as a single object, they're much larger than the solar system. The largest one can be about 100 times the size of the solar system in one single object. And here is some radiation that from all the light that go around that is bent, and also the hot plasma falling in. So that just give you an idea of the scale. So these are the largest engine in the universe. And yeah, you would expect that these produce a bit of gamma rays. So now, let's look at the same image in gamma ray, and it's anticlimactic. Okay. Yeah, that's very disappointing. But when this was taken, it was a huge discovery. It was the first time that we see it's not just a single point. Actually, it's a potato shape in the direction of the jet. You see there is kind of this direction here, and exactly the same direction of the jet. So that shows that we know that gamma rays come from the core, but also from farther away in the jet. We still don't know exactly where they're coming from, but that was a very nice observation. So yeah, we don't have the resolution. So complicated technology, we still don't have the resolution to do the same as the optical. Okay, now a bit more science, particle processes. How do you produce gamma ray? And people have been working for decades and decades on that, and they already have some idea. So here is a spectrum of one of these AGN. So it's the amount of light received per unit of frequency. And you will see that these things radiate from radio wave up to very high energies. These are one of the very rare objects that radiate over the full electromagnetic spectrum. And there's two single bumps here. There is one that peaks in X-ray, and another bump here that peaks on gamma ray. So we are pretty convinced now that the synchrotron emission is responsible of that, which means you have charged particles. We have very large magnetic field in this jet, and as I mentioned before, the particle is going to rotate around the line of the magnetic field, and this rotation actually emits light. We call that synchrotron emission, and we can explain this very well. And for the second one, we are a bit less sure, but for most of the targets of the source we observe, we're relatively confident that this is inverse Compton. So what is inverse Compton? Is like a BR pool game where you have a fast-moving ball that's going to hit a slow one and just transmit its kinetic energy. So here you have these high-energy particles that's going to impact a low-energy photon and going to transmit its energy to the photon and accelerate it to, should be careful with that, toward high energy up to gamma ray. So okay, now we have an idea of the process that still doesn't tell us where does that come from in the jet. And it's better now to look more into higher resolution. This radio telescope can achieve extremely high resolution. I mean, that's where we see this black hole. And we see this motion. See the scale here? These are the years, 2003, 2004, 2005. So these guys have been observing this source for 30, 40 years now, and what they see is there is things that are ejected here, that are moving, tracing through the jet. And here's an example of how you put all this in one single image between 1995 to 2020. So this is Mojave collaborations, collaboration that use radio telescope in the US. And you see that all these ejectors, this is the distance from the core. They're ejected at a very fast speed. And there is other very interesting stuff we know this, and we observe this source in gamma ray. And here I give you an example of something that happened really by chance with the Veritas telescope. So there have been these multiple radio observation, and they see some stationary features, especially the radio core, and they started to see a moving thing, so something ejected from this source. The name of this source is BLAC. And perchance we were observing it with Veritas one night, and we've seen a very big flare. And the full time scale of that is about 2 hours. So you have this thing that are many times larger than the solar system that can erupt just in a few hours. And this happened, so we observed it. Of course, we see that the flux was very high, so we stayed the full night on it, because we're, wow. And then when we wanted to publish a paper, we look at other wavelengths, and we were like, oh, that's very interesting. This happened exactly at the time where this thing was crossing what is called here A0, which is the core in radio of the source. And this tells us a lot about what happened, what was the process that accelerate particles and emit gamma rays. So this is a scheme. Actually, this was done back in the day, 1985, and these guys were very lucky that they really find a scenario that still work very well. They're pretty good too. And they're like, well, yeah, we should have very strong shock close to the core, but 1 parsec. 1 parsec is about 3 light years. So when I say close, you have to keep in mind astronomy. And this shock, when you have perturbation going through it, then it triggers a flare, and then you see something moving down the jet. So now the next question, if you're curious, I still haven't explained how you accelerate particles. We call that the Fermi shock or diffuse shock acceleration. So let's say you have a shock, which means that if you look at the position of the shock, before the shock you have a fast flow, after the shock you have a low flow, and if you have a particle that just has the good idea of just bouncing back and forth around this shock, when it bounces here, it's going to be kicked pretty hard with a very fast flow, okay? So you have this little guy in the rocket, and the fly, actually, that's showing me the... And when it's going in this direction, it's going to be bounced back in the other, but with a slower flow. So here it's going to gain a lot of speed. Here it's going to lose a bit of speed. Here it's gaining a lot, losing a bit. So if you gain a lot, you lose a bit, then you gain a lot, right? At the end of the day. And this really accelerates particles. And this have been simulated, really do numerical simulation. And this is very efficient. So then the next question is, how do you create these shocks in the jet? I mean, the jet is moving super fast. How you have a stationary shock that just don't move? So there is few recipes, and here we're getting closer to my very narrow field of study about these sources, which are about the study of this shock. So you need few conditions, and if you fulfill this, you're good. You need to have supersonic or supermagnetosonic flow. You need to have some pressure difference between the inside and the outside, and you need to have something that trigger the shock, so like a local severe pressure drop. If you fulfill all these conditions, these are numerical simulation, you can reproduce these beautiful shocks here we call recollimation shocks. You can also produce them on Earth. Here, you can have all these conditions in Earth, especially in the exhaust of rockets. So I'm just showing you here just a video of a test, engine test of a rocket booster here. And you see you have this diamond shock here. So this flow is very fast. It's a supersonic flow, but these structures here are stationary. And in this, you can accelerate particles. So you can imagine that the AGN is the same thing, but at the size of a supermassive black hole. And you can also do the simulation. Here I work with a student at the Paris Observatory, and we reproduce this with MHD simulation. So it's simulation of a radio jet with stationary shocks, and we throw some ejecta in it, and we see that the flux indeed show flares. So this is working very well. Okay, so I'm going to stop around here, just opening to the future. We want to increase our resolution. Of course, you see that we don't want to see potato in the sky. We want to see things much more defined. So far it's been, the current generation have been operating of about 20 years, but it's been already several decades we're preparing the new generation. So there is the CTAO Observatory. We're going to have 2 arrays of tens of telescopes in the north and the south hemisphere, so we could observe the full sky. And they already started building it. It should be operating starting 2027, and the sensitivity at least will be about 10 times more than the current we have. So stay tuned about that. And just to finish here, I'm very happy to show you all my students with a big smile at the Lick Observatory. I'm not sure you can visit this one. It's a very big one, the Shane telescope. But for them, as undergrad, it's really a life experience, and I'm very glad that I'm able to do this. Okay, thank you very much.
Okay, so we have time for some questions. If anybody has anything on their mind, I'll hold a hand back there first.
The difference between Hubble telescope and the one like this one, for example. Well, the Hubble telescope is, actually I will go back to some of my first slides, because that's where I kind of cover it, sorry. Here. So the Hubble telescope is very similar to the Lick telescope, like you're probably going to see the nickel, right? Maybe. Okay. Maybe. Just a reflector telescope. So you have a mirror. The shape of the mirror is going to condense all the light to a single point. So that's going to amplify. It's like you have an eye that's several square meter. And that means also that you can just have all the light from a very narrow part of the sky. So you amplify the signal, and you also amplify the resolution. So the one we use is more like this kind. We cannot use, we cannot use mirror just for the optical light. What we want to detect are the gamma rays. And as I mentioned before, the gamma rays don't reach the ground. They produce these showers, but these showers produce a flash of light. And this flash of light is going to go to the mirror here, like this, and then be bounced toward a very fast camera. So that's that different technology. Here we need to have camera that take picture at a nanosecond scale. Okay, so, and that's Hubble, don't do that. No, I mean, now both are extremely efficient in their own energy domain. I mean, as I showed before here, like if you have Hubble, you can just see that. But if you have other telescope, you can see that. So which one is the most efficient? They're both necessary to understand the big picture, right? Okay, more question? Yeah?
I'm assuming our galaxy does not have an active galactic nucleus. Is that right?
Yeah, it has a supermassive black hole. Actually, we have only 2 images of supermassive black hole, the one of M87 and the one of our own galaxy, which are very similar if you look close by like that. But our galaxy has been active in the past. Actually, we see some traces of jets that were here millions of years ago. Actually, as soon as something is going to fall in the black hole, it's going to restart the activity. So most of the evolved galaxies, like the one we are, basically the black hole has cleaned everything around. All the gas around, the dust has been already cleaned. I mean, basically fall in the black hole. And now there is not much more. So one thing that can restart the galaxy is like galaxy merger. For example, we're going to impact Andromeda in millions of years. And this is going to really brass everything, move the gas. And at some point, even the 2 black holes are going to merge together. And this very likely is going to restart an AGN from our own galaxy.
If we did have an AGN, would that be dangerous?
That would depend where you are. I think we would still be safe because we are pretty far away in the disk. That means there's a lot of dust and between us, but still, we'll have much more radiation. So at some point it will be dangerous, but life on Earth, I think, should still be okay. Yeah?
On the antenna array, how do you know that the light you're detecting is from the gamma rays?
Compared to cosmic rays,
So when you're,
I would,
you have that burst where it kind of separates, and you're saying
yeah.
it generate light because the gamma rays went faster than the speed of light, right? So
Right.
that's the result. How do you know that's? How do you ensure that what you're detecting is that light, not something else?
Well, first, there is not many processes that can create 1 or 2 nanosecond flash, if you think about it. It's impossible to create this flash from natural things. And the fact that actually the fact that our method of reconstruction work somewhat show that this is gamma ray. What is the tricky point is really about making the discrimination between this and that. Because these are cosmic rays, and all direction is really background. We don't want them. And these are gamma rays. The issue at low energy in our instrument, you have 1,000 more than this of this and that. But they produce slightly different image on the camera. So I didn't show this, but you have slightly different image. And these days, we use machine learning to discriminate between the image to select only the gamma rays to be sure that we are not polluting our signal with all of these showers. Yes? Well, it depended also in what wavelength. There is actually the scale of universe you can observe in gamma ray. It's very interesting. Is not as large as the one you observe in optic. Why? Because these gamma ray, when they travel the space, they're going to interact with the radiation field from the stars. It's the optical radiation from the stars and dust. And actually, you can have this process happening, kind of. I mean, you will have the split in gamma ray to electron positron in the universe. So the farther you are away, the more you are absorbed, the more your universe absorbs gamma ray. So the distance is redshift 1 for very high energy. I don't know if it really speaks to you, but it's no more than a few billion light years. Right.
Maybe one more question, and then we'll be here to answer questions afterwards, too.
How long did it take to get the black hole picture?
It took a long time. I mean, I think in terms of observing in the sky, it was probably around weeks in total, accumulated weeks to months. But the issue was to create this picture that take years, because it's very complicated. The issue is here. You have an array of telescope scattered through the full surface of Earth. And you need to, this is interferometry, that means you need to synchronize each telescope at the microsecond scale. And this is extremely challenging if you have one telescope in Antarctica and another in Europe and another in the US. But in terms of exposure, I think it's weeks to months. I'm not fully sure though.
I'm sorry, one more question.
Yeah.
The Vera Rubin, is that going to affect your ability to zoom in on gamma rays as they're emitted? Because it's supposed to be online, like they're releasing that in real time almost.
I mean, it's going to help us a lot because most of, for example, this AGN, when they flare in gamma rays, they also flare in optic.
You'll be able to catch them easier.
So the thing is, the Rubin will scan the sky very quickly.
Yeah.
And then they will, and there's already all the pipeline that are developed, the alert pipeline between all telescope on Earth, where if they detect like a factor 2, factor 3 larger than what it's supposed to be, we receive like an alert a few seconds or a few minutes later, and we can directly point on it. So yeah, you're going to be, it's going to be very useful. The only issue is the Vera Rubin is South Observatory, and we're in the north, so there's not much sky that we can see together. Yeah.
Please join me in thanking the speaker again.
Thank you.